When it comes to rates of change, we already know how to find an average rate of change, and we already know how to approximate an instantaneous rate of change. If you're not sure how to do this, watch this video here. But now we have a new method, and this new method is called using the difference quotient. So you're going to hear your teachers talk about the difference quotient quite a bit, and it's really just a formula we can use to calculate the exact instantaneous rate of change. So I'm going to show you two things. One, where this difference quotient formula comes from, how we can find it, and then I'm going to show you an example of how to use it. So let's say we have a graph, and I'm going to draw an XY axis here, and I'm just going to focus on the top right quadrant like this. So we have our X and Y, and the graph is going to look something like this. I don't have the equation for it, but it kind of looks like either an exponential function or the right half of a quadratic. That doesn't matter. It's just a curve that we have. Now let's take 2 points. We'll take a point right here, and we'll take a point over here. Now each of these points has some coordinates. This first point, I'm going to say it has an x value of a. And if this graph has the equation representing it, we'll say f at x, then we can say that the y value here at the point that has an x value of a is going to be f at a. Right? We always plug in an x value for x into our equation to find the y value. So this point right here has the coordinates, and I'll put a little arrow, a, f at a. Those are the x and y values of that point. Now we can do the same thing for this point over here. One thing, though, that I want to make clear is that the distance between these 2 points in the horizontal direction, so the difference between a and this x value over here, that distance I'm going to call a distance of h. And if I do that, and this value here is a, then this value over here will be a plus h, because it is a value of h greater than a. So this x value is a, this x value is a plus h. Okay? And if that's the case, the y value, we can just as easily say, is f at a plus h. So this point has the coordinates a plus h, comma, f at a plus h. Okay, so once we've done this, what we can do is we can discuss the slope between these 2 points. And remember, to find the slope between 2 points, you just draw a line, you do your rise over run, right? Rise over run, in other words, is the change in y over change in x, delta y over delta x. Now, what is delta y? What is the change in y? Well, we subtract this y value minus this y value, right? So we can say it's f at a plus h minus f at a. And what's the change in x? Well, it would be the a plus h minus the a, right? We subtract those two x values. So we'll have a plus h minus a. Now what happens here? Well, a minus a, those will cancel one another out, and you're just left with h on the bottom. So I can say that all we're left with here is going to be f at a plus h minus f at a, and this is all over h. Now, what this gives you is the slope between these 2 points, right? We all agree on that. Now, what would happen if this value of h, the horizontal distance between the points, got smaller and smaller? Well, if the points got closer together, you'd have a slope like that. If they got even closer together, like this, or even closer together to the point where they're actually the same point, well then that average slope, that average rate of change between them actually becomes an instantaneous rate of change, because those points become the same point. Well, when those points become the same point, the value of h has shrunk to a value of 0, right? The gap between the points becomes 0. And so what we can do is we can take a limit of this thing over here as h approaches 0, and that will give us the instantaneous rate of change. So we're going to take the limit of this thing as h approaches 0. This is what we call the difference quotient. And this is the formula you can use to figure out the instantaneous rate of change at any point for any function. If you haven't done a lot of work with limits or you forgot about limits, watch this video over here. Now let's do an example like I promised we would. Let's say we have f at x is equal to x squared. So the parent function for quadratics. And let's say we're asked to find the instantaneous rate of change at the x value of 3. Okay, let's think about this. We have our difference quotient. It's the limit as h approaches 0 of f at a plus h minus f at a divided by h. Now, what is f of a and f of a plus h in this example, in this context? Well, f of a is just the x value that we're dealing with. Here, the x value we're dealing with is 3. That's the location that we're interested in finding the instantaneous rate of change. So a is going to have a value of 3. The function we have, f of x, is x squared. So wherever you see an f and then a bracket, that function has to be represented with an x squared. So what I'm going to do is I'm going to say we have the limit as h approaches 0 of, instead of f of a plus h, I have to write this function, x squared, but instead of x, I'm going to substitute in a 3 plus h for x because it says a plus h has to go where x is. So I'm going to say 3 plus h squared. And I'm going to subtract f of a. Again, the function f of x is x squared, but I'm going to plug in the 3 because 3 is what our a is. So it's going to be 3 squared. Okay? And this is all divided by h. Now, what do we do next? Well, we have to evaluate this limit. We have to figure out what it equals. Now, if you remember doing limits, the first thing you can try to do is plug in the value that we're approaching. But if you plug in 0 for h here and here, you end up dividing by 0, which is a no-go. We can't do that, right? That will give us a value that is undefined. We don't want that. So we have to do something first. So that limit can't be applied just yet, so I'm going to keep it here. Now let's look at this. Well, we can do some expansion, I think, right? We can expand this binomial, right? It's being squared. And if we do that, you'll have 9 plus 6h plus h squared. And then over here, you'll have minus 3 squared, which is 9, all divided by h. And if you're not sure how I'm expanding this into this, just remember, if you have a binomial squared, that's 3 plus h times itself, 3 plus h. You could do FOIL here, right? You multiply the first terms, the outside terms, the inside terms, the last terms. This is grade 9 math, right? We expand this using FOIL, and we're going to end up getting this as our answer. Now, we can simplify a little bit. We have a positive 9 and a negative 9. Those cancel one another out, right? 9 minus 9 is 0. And you see that what we're left with here are two terms on top. Each have h as a factor, and you have an h on the bottom. Well, what that means is we can divide this h from each of these terms, right? We can cancel out an h. This h cancels with this h, and we'll cancel out one of the h's in this term, which will get rid of the square. And what that means is we're going to be left with the limit as h approaches 0 of 6 plus h. Now we can evaluate the limit. Now we can plug in a 0 for h. If you do this, you're going to have 6 plus 0, which simply gives you 6. Meaning that the instantaneous rate of change at an x value of 3 for the function f of x equals x squared should equal 6. In other words, if you have a graph like this, nice little parabola, right? This is y equals x squared, I'll say, at a value of 3, if you draw a tangent line to the curve, so a straight line like this, and you take the slope of that line by doing rise over run, the slope you get should be equal to 6 exactly. And that's not an approximation, that's the exact value. If you tried to approximate it by taking two very close points, like a point right there and a point right next to it, like we did last year, then you would get a value very close to 6, maybe 6.001, and you would assume the value is 6. Now you can use the difference quotient and get that exact value. This is actually the foundation for all the work you're going to do with calculus this semester. So when we take derivatives, derivatives are just another way of figuring out the instantaneous rate of change at a point. So you'll see the derivative rules in the next few videos, and you'll see that they yield the same type of answers as you get in this example here.